start with an hour's sort of introduction to linear optical quantum computing, bearing in mind that it's the same physics that applies to all photonic quantum technologies, in the sense that the way we analyse these linear optical circuits is the same whether we're looking at things for quantum metrology or for quantum communication and so forth. And maybe you can just tell me what you've done so far in terms of quantum computing.
What in some schools so far?
Yeah.
Well, we've had people talking about ion trap, quantum computing, cold atoms, although less so for quantum information processing.
Diamonds, MV centers?
Yeah, MV centers also.
Who told you about MV centers?
Peter and I talked just a little bit about sort of quantum optics implementation, so more towards metrology, I guess, as well.
So you've all seen this list either earlier in the summer school or previously, that to build a quantum computer, you come up with this list, which is very much the same as the list that you dream up yourself in a couple of minutes if you thought about it, in the sense that if you thought about how a conventional computer worked and map that onto how a quantum computer might work, you obviously need some qubits to code the information. We explicitly say that you need low noise in contrast to a conventional computer where the error rate is 10 to the minus 20 or something like that, and we just don't worry about noise. And you need some fundamental logic gates, which we typically break down into 1 qubit gates and a CNOT gate or some other entanglement gate. Initialization, so you need to compare your register in the all zero state, for example, and readout. So it's a fairly obvious list, and these go by the name of DiVincenzo's criteria for quantum computing. But as I say, anyone who had a sense of how a conventional computer works would dream this up themselves in a few minutes. And so, I guess for any implementation that you can imagine, this turns out to actually be a somewhat contradictory or confounding list of requirements, in the sense that having low noise means that you have low noise qubits means that you have a quantum system that's very well isolated from its environment, so it doesn't interact with anything around it. But then it interacts very strongly and very precisely with other qubits to realize some sort of 2-qubit gate, and it interacts very strongly with your initialization and readout apparatus. And it turns out that with just about any system that you would imagine trying to build a quantum computer out of, you go through this list and you get very happy and you put big ticks next to some of these things, and then one of them turns out to be a bit of an issue. And I guess to highlight that, if you think about single photons versus the spin of an electron as your possible qubits, then in the case of both of them, you have in theory a model 2-level system. So, for example, the horizontal and vertical polarization of a photon with a spin-up, spin-down state of an electron. But then, in the case of a photon, you have a very low noise system, as I'll elaborate on in a little bit of detail. But essentially, you can send a polarized photon to the moon and back, and it'll still be in that same polarization state. My colleague at Bristol, John Rarity, likes to say that the lifetime of polarization encoded photons is at least the age of the universe, because the microwave background radiation is polarized, which is a fair statement. Actually, I think that there's going to be working space to take full advantage of that. But then when it comes to single electrons, you know that you've got a spin, and it's going to be affected by any other spin in its environment, any other magnetic field in its environment. It happens to be sitting on a charge, which is affected by any charge or any electric field, so it very rapidly decoheres or very rapidly loses its quantum state unless you take special precautions. And then if you think about gates, in particular two-qubit gates, how do you get these things to interact? Well, it's very hard to get photons to interact with one another, as you know from just thinking about shining two beams of light across each other from two torches or flashlights. You know, you're not going to get much reaction. Whereas with two electrons, it's very easy to get them to interact. Two electron spins, you just bring them into proximity with one another, and you've got dipole and exchange forces, and so on. And I think that's the, you know, probably the two ends of the spectrum in terms of you know, very low noise and very easy to interact is photons and electrons. And then the same sort of things go with initialization and readout. So does that make some sense what I'm saying there about these being almost a contradictory listing requirements? There's lots of people with their eyes open, and there's one person awake back there. So what I propose to do is to spend the next little while just giving you a sort of introduction to quantum computing using photons, and then we'll over the next two sessions we'll take it from there. I want to emphasise that all of what I'm saying is applicable to any sort of anything that you might want to do with photons, whether that be for quantum metrology or, you know, doing experiments to explore the foundations of quantum physics, whatever it is, it's the same physics that applies basically. So I'll go through this list because it's vaguely helpful. You could imagine, for example, the polarization of a single photon as being a nice qubit. You could send this thing along here. As I already said, this is an intrinsically very low noise system. Terry likes to highlight the fact that these things exist at zero temperature, so effectively at zero temperature, an optical photon, and that's in contrast to any other system that we know of that exhibits quantum mechanical effects, which is always coupled to some sort of thermal path. So that's the sort of the qubits and the low noise, if you like. Realizing one qubit gates is relatively straightforward. We can use a sequence of optical elements, which we typically call wave plates, which are just materials whose refractive index is different for two orthogonal polarizations. So quartz is an example of this, a material where the light propagates at slightly different speeds for two orthogonal polarizations. And these are, you know, standard elements for manipulating the polarization of a bright laser beam or, you know, bright classical light, if you like. The same sort of thing that you find in, you know, in a polarization filter for a camera or polarizing sunglasses or so on. And it's often claimed that these that one of the key advantages of photons for quantum information is that you can use off-the-shelf components. You can just go and buy these wave plates, these optical elements. And I think that's true, but I'd argue that that's the same, for example, for the spin of an electron. You can use the same electromagnetic fields to manipulate the spin of an electron. What's really important, actually, is the ability to calibrate those systems. And that's what's unique about single photons, is that you can send a bright laser beam through here with exactly the same characteristics as your single photons. So the same polarization, same frequency, same bandwidth, etc. And you can precisely calibrate these things, with 5, 6 nines precision. Does that make sense? And I think that's really the unique thing in terms of conventional optical elements, is that you can really basically trivially calibrate it. You can trivially work out what the angle of this thing is, and a sequence of these things to do any 1 qubit rotation, any 1 qubit operation that you want. So a 1 qubit unitary is very straightforwardly implementable and very precisely calibratable. And then, in terms of initialization and readout, well, initialization, if you prepare some known polarization, or you send your photon through, for example, a polarizing beam splitter, which transmits the horizontal and reflects the vertical component of the light, then you can prepare a particular state. And actually that's the same thing that you'd use for readouts. If you put a single photon detector here and here, you can realise a measurement in the computational 0, 1 or HV basis. So you think of this as the 0, 1, for example. Can you all see that from the back? Yeah, sort of. I'll try and write a bit bigger. So that leaves us with how to realise 2 qubit operations, for example, a CNOT gate. And as I've already alluded to, that's very challenging with single photons. It's very challenging to get them to interact or to effectively interact with one another. I guess you're all happy enough with this idea that you need some sort of universal set of logic gates. So just as this PC here at its most basic level is implementing just a series of very simple logic gates, in terms of a quantum computer, we'd imagine doing the same thing, realising a set of 1 qubit rotations and a particular 2 qubit entangling gate. It doesn't have to be the control NOT gate, but some sort of entangling logic gate to build up any algorithm. Is that roughly a familiar concept to you? And so, as I said, the reason that you already know this is hard, and in fact everyone knows this is hard, is that you imagine taking 2 flashlights or 2 torches and shining the beams across each other in some sort of trivial experiment, and nothing much happens. And if you think of those as beams of particles, then it's in contrast to any other sort of particle that you know of, where you'd see some action of some sort. And so it's this interaction between photons that's the real challenge. And I guess I want to just sort of now start by sketching out in a bit more detail why that's challenging, and then tell you about a solution to that problem that was developed about a decade ago, and then sort of bring it up to today. So you know that a CNOT gate, we have a control and target. As input and output. And that this is the sort of logic of that operation. So we talk about a control and target in the sense that the target qubit has a bit flip operation on it, conditional on the control bit being in the 1 state. And for those of you familiar with this, it's of course just the classical XOR or exclusive OR operation. But of course this table goes on with an infinite number of input states, as you can put superposition states in here, so I should make it clear that these are quantum states. I can, for example, put the control in superposition of 0, 1, and then at the output I'll get a superposition like this, which is obviously a maximally entangled state of those two qubits. And that's, you know, the entangling power of the gate. Anyway, so it's actually sufficient to think about the you know, the four computational basis input states for what we're doing, but bearing in mind that being a quantum gate, you know, any superposition states are also possible. So there's an infinite number of input and output states. So let's think about how we might go about making such a gate using single photons. Now I want to emphasise here that you know, we've encoded in the polarisation of a single photon, and then we've sent that single photon to a polarising beam splitter, which separates the horizontal and vertical components. And in fact, you can thereby realise a superposition where you have now two modes, two spatial modes or two paths, and you now have a superposition of a photon in this path and in this path. And I hope you can quickly convince yourself that you've mapped exactly the same sort of logical state from polarisation into path. Does that make sense? And it turns out that you can do the sort of reverse operation as well, and go back to the original polarisation state here. And conceptually, it's often very convenient to think about things in this path encoding, and in practice, as I'll hopefully get on to maybe in the next hour or the one after, in practice in these waveguide chip devices that we use, it's very practical to use this path encoding. But conceptually and mathematically, it's exactly equivalent to encoding in these two ways. And I think for the remainder of the talk, I'm going to talk exclusively about this type of path encoding. So is everyone happy with that? Jean, are you happy with that? So how do we realise a controlled NOT gate? So we've got our control qubit. If it's in this path, it's a 0. If it's in this path, it's a 1. And we've got our target qubit. Similarly encoded in path. So we look at the target qubit. We could imagine putting that on a 50-50 beam splitter, so a half-silvered mirror, a device that reflects half the light that's incident on it and transmits the other half of the light that's incident on it. So that if you send a bright beam of light in here, half of it would be reflected and half of it would be transmitted through here. And then we do the same thing again. And if we send the logical 0 state, by which I mean a single photon in here, what happens to it after this first 50-50 beam split? What's the state afterwards?
Plus this.
Plus. Okay. And if I send a single photon in here, which is the logical 1 state, what's the state after the beam split? Okay, and then what happens to this state at this second beam split? Goes back to 0. And why is that?
sorry, I'm a theorist, beam split is a self-inverse. So I would say you probably have a better explanation than that.
You don't always have to apologise for being a theorist. It's not always a point. It goes back to being a zero, because if you're a theorist, then you know this is the Hadamard operation, and you know the identity. You know you know that the Hadamard implemented twice is the identity, and if you're an experimentalist, you know that it goes back to zero, because this is nothing more than interference of waves. It's the classical interference phenomenon where you imagine, you know, you send in some wave here and you split it in half, and it recombines here, and it interferes constructively to come out here and destructively to come out here. And what happens here?
One.
And why do I get this minus sign here?
Unitarity.
I like that explanation. Yeah, unitarity. Yeah, any other explanations for that?
The phase shift on the one side being separate.
Yeah, so you can have a number of nice explanations for this. Unitarity means that you send in orthogonal states. It's some unitary operation. So you should get orthogonal states out. So that means that these two things, you know, you should have an e to the I of phi here, but that gives you a number of possibilities. If you look at the sort of microscopic detail of how you'd realise one of these beam splitters, then you see that, you know, you've got layers of dielectric of different refractive indices and so on, and that you remember that when you get a reflection from a higher refractive index off of a lower refractive index, you get a phase shift. And the third nice physics reason is that if you don't have that phase shift, then you end up getting more light out of these things than you put in, violating conservation of energy. But maybe for the purposes of this summer school, we can just think of this as being some unitary, and we should get a phase shift. And we can work. Obviously, this is in some sense, well, in a precise sense, that's the definition of what this beam splitter does, and we can work out what comes out here by just applying this transformation again. Is that okay up to that point? And so, from a logical point of view, we've done nothing here, right? We've mapped a 0 to a 0 and a 1 to a 1, and by some sort of linearity of quantum mechanics, we've mapped any superposition of those two states to the same superposition at the output. So logically, we've done nothing. And if the control qubit now is in the 0 state, so we have a single photon here, then we're in the top half of this table, and that's precisely what we'd like to do with the target. We'd like nothing to happen to it, as you see it in this up. And again, you can convince yourself again by a linearity argument that if we worry about these four input states and we get that right, then we've got everything right. If, however, the control qubit is in the 1 state, we're in this bottom half of the table here, and we'd like the target qubit to have its logical state flipped from a 0 to a 1 or vice versa. And we can imagine doing that by implementing a pi phase shift or a half wavelength increase or decrease in the optical path in one arm of this interferometer. And what that will do is change this to a minus and this to a plus. And that will change this to a 1 and this to a 0. Does that make sense? So if I I physically change the length of that of this distance here by half a wavelength, and I'll go from a constructive interference for a photon coming in here to a completely destructive and constructive interference out here. It's just again a classical interference. And what I'd like to achieve here is to do that, to have a pi phase shift or a half wavelength increase in path length conditional on there being a single photon in this path here. And roughly speaking, again looking at this table, I don't want anything to happen to the control here, so I can just let it propagate. And I say roughly speaking because obviously you can see from this input that the control qubit here enters in as a superposition of 0, 1 and is then 1/2 of an entangled state, so it clearly does change, but again it's sufficient to think in this picture. So that's the solution to a controlled NOT gate for a pair of photons encoded in path. And I hope that it's clear from this earlier discussion that, you know, if I started in polarization, I'd just put one of these things at the start here and here, and if I wanted to end in polarization, I'd just do the same thing at the back. Does that make sense so far? So that's the problem solved. You just need a device that implements a pi phase shift on a single photon, conditional on the presence of a single photon here. And so the idea that you immediately come up with is to use some nonlinear optical material. So a material whose refractive index depends on the intensity of light propagating in that material, such that the intensity of this single photon will affect the refractive index that this photon sees. Now, nonlinear materials are common. You don't normally think about them when, for example, you apply Snell's law to a pane of glass or something, and you're calculating the angle. You don't have to say, well, what's the intensity of the light in it? Most optical materials that we think of aren't linear materials. But there's plenty of examples of nonlinear materials like this. But it turns out that if you were to have such a nonlinear material whereby a single photon would impart a half wavelength or pi phase shift on a second photon, you'd need something like 10 to the 9 meters of the strongest nonlinear materials that we know of in order for this to happen. And that's not completely infeasible in the sense that you might imagine a spool of optical fibre 10 to the 9 meters long, where you send these two photons through, and if this photon's there, then this photon sees a slightly higher refractive index, and after 10 to the 9 meters that accumulates a high phase shift. But of course nothing's that transparent that you have a very high probability of getting either of the photons out at the end. And so this is a kind of this was the intuition that told people that linear optical quantum computing is impossible because of this fact that it's very hard to get at. I mean, this is not a proof of anything. It's just a sort of sketch of why it's hard for one photon to interact with another. And so what was widely understood up until around 10 or 12 years ago was that you'd have to have some sort of, for example, an atom cavity system here where you'd have some, for example, two-level atom that would mediate an effective interaction between those two photons. So this photon would come in and this photon would come in, and depending on the state of that atom, this photon would see a different a different state of the atom. So the idea being that, you know, a single photon can interact very strongly with an atom or an atom-like system, whether that's a quantum dot or an NV centering diamond. And both of those photons can do that, and thereby the single atom-like system can mediate an interaction between the two photons. And this is, you told me already that someone's told you about NV centers. I don't know that they told you in this context, but you know, real single atoms in optical cavities, NV centers, semiconductor quantum dots. There's a whole host of systems where people are exploring exactly this type of thing. But for the remainder of this talk, I don't want to go into that anymore at all, except just to say that that was the understanding up until around 2000, that you'd have to have some sort of system like this in order to mediate an interaction, to realise this interaction that we've just sort of, I hope, convinced ourselves is hard to achieve. So any questions up until that point? Am I stopping on the hour?
Yeah.
Yeah. So in 2001, Keneal, Laflamme and Milburn came along and they said, actually, you know what, you can realise one of these C0 gates if you have your control and target photon here and here, and you introduce some auxiliary photons, so photons that essentially act as catalysts in this operation. They don't encode information going in, and you have some linear optical network and single photon detectors, then you can get a controlled knot operation, precisely this operation between these two photons. And this seemed to contradict this intuition that I've just sketched out for you here. Terry may know more of the story, but as I understand, Keneal and Laflamme set out to prove this intuition, to prove that you couldn't realise a large-scale quantum computer, for example, using single photons and linear optical networks alone, and in the process proved something far more interesting, which is the opposite, that you could. You know the story, Terry. That's how it goes, apparently. And as I say, it very much contradicted this intuition and was a pretty exciting result, because it showed that you could realise, a full-scale large, arbitrarily large fault-tolerant quantum computer using the resources of single photon sources, a linear optical network, by which I mean just, a multi-photon, multi-path interferometer where you'd have, a bunch of these beam splitters and photons propagating along some paths, but no exotic kind of non-linear elements at all. Nothing particularly fancy. Just a simple network of beam splitters and so on, and single photon detectors at the end. And the idea of this gate is that it doesn't work with probability 1, which maybe is a bit of a problem. So you're surprised that you can do it at all, and maybe not surprised that it doesn't happen with probability 1. But you know for sure whether it works or not if you get one photon at each of these outputs. So you send these 4 photons in, and if you get a single photon at this output and a single photon at this output, then you know that it's worked, and out here comes your control and target photons with the C0 gate implemented on them. Now, of course, a logic gate that doesn't work with probability 1 is useless for a quantum computer, right? Because you if you have n of these things, you very rapidly have near zero probability of all of them succeeding together. So that was the first problem, and that was a problem that was, I guess, already solved by Gottesman and Chuang, which was to show that you could do teleportation of these gates to make things work. I want to spend a few minutes explaining that to you. So this is just a cartoon of the operation of these things. I haven't told you what goes on in there. I'll get onto that perhaps in the next lecture. But now what I want to do is tell you how we address the problem that these things don't always work. So we call them heralded in the sense that if you get this single photon detection here and here, you know that it's worked, and if you get something else, you know that it hasn't worked. So it's probabilistic, but you know whether it's worked or not. And I don't know whether you've gone through quantum teleportation in this summer school. You don't know either. But I'll just sketch the idea, which is very simple. So if I have some arbitrary single qubit state, and I have another maximally entangled state of 2 qubits that we just conventionally write as the phi plus state here. I'll just kind of use that picture to indicate that, you know, they're entangled when they start together. If I do a measurement of these 2 qubits in the Bell basis, which if I extend this picture here, then that's these 4 states that I've just defined here are the 4 maximally entangled Bell states. And so mathematically, those 4 states are just as good as any other basis for measuring 2 qubits in. Just as, for example, these 4 states are a perfectly good basis in that, you know, it's an orthonormal set of states that span the space of 2 qubits, and at least mathematically they're exactly equivalent to one another. Physically, these are you know, interesting in that they're maximally entangled states. But anyway, in any case, I can for sure measure these 2 qubits in principle in any basis that I like, and I choose this basis as I've just defined here. And then depending on which of those 4 states I measure, so whether I measure the phi plus or minus or the psi plus or minus states, I may or may not do a bit flip operation and a phase flip operation here, where, you know, the bit flip just does that, and the phase flip does that. And if I do those operations according to some predefined table of the outcomes, then I get the same state psi out here. So I think this is probably familiar to most of you. This is the idea of quantum teleportation, and of course it has this great sort of Star Trek sounding name to it, and it's very interesting in the sense that if you think about what you know about quantum physics, then you conclude that, well, it should be impossible, right? Because to teleport the state of something, you'd need to determine what that state is and then reconstruct it in another place. And what you see fairly explicitly here is that you do precisely the opposite of that. You learn nothing about this state psi. You must learn nothing about that state psi, so you don't know what it is before or after this operation. And of course, you could never determine exactly what that state was and reconstruct it if you were to go about it like that. I guess this is familiar to most of you. Is that okay? Okay, so now imagine that this is my control qubit here. Then I'd obviously get my control qubit out here, and I could do exactly the same thing with my target qubit. I could take another maximally entangled state, do some sort of Bell state measurement, and depending on the outcome, I could do my bit and phase flip operations here. Perhaps I should just before I do that, I should just quickly explain what's going on here. I think it's familiar to everyone, but just in case. So if this is my unknown state psi, then I can label these qubits 1, 2, 3, and you can see explicitly that this qubit is written in the 0-1 basis, and these two qubits are written in the Bell basis. And what I can do is I can write that same state where I write the first two qubits in the Bell basis, in this basis that I've defined here, and the third qubit in the computation basis. And if I do that, which is just a few lines of algebra, then I get something like that, where I haven't got the amplitudes that will come from the some combinations of alpha and beta here, but you see that it's just a algebraic rewriting of this state in a different basis, and then I'll have some alphas and betas in front of all of these terms. So you should, if you haven't already done it for yourself, you should spend 5 minutes and go through and do exactly what I'm sketching here and write this state in this other basis. So I've gone from writing the state where the first qubit, this one here, is written in the computational basis 0 and 1, and the second two qubits are written in the Bell basis, the phi plus and minus, psi plus and minus maximum entangled states. So writing the first two qubits in that Bell basis and the third qubit in the computational basis. Does that make sense? Yep. And then it's pretty straightforward to see that if I measure the first two qubits, 1 and 2, in the Bell basis, then I'm either going to get one of these 4 states, and depending on which one I get, I then have the third qubit already in the state psi, or I have it in the bit flipped version of psi, or the phase flipped version, or the bit and phase flipped version, and then I know that I should do one or other or both of these operations, because obviously another bit flip or another phase flip undoes the first one. Does that make sense? Okay. So if you haven't done that, you should do that. It should be 5 or 10 minutes to go through and convince yourself that this is a simple operation. Now I think it's interesting. I don't know if other people have a perspective on this, but it's high school algebra, and yet it was decades after the invention of quantum physics that this was recognised as being a feature. What's your take, Terry? Have you got your eyes open? No.
I wish I was.
But it's, you know, it's really trivial to see, and yet I guess conceptually very strange. But yeah, it's a really interesting feature of quantum physics that has important applications, particularly in communication. And the one that I'm going to show you in the next couple of minutes, I think, is a really interesting application of this quantum teleportation. So that's the idea. So now, what have I got? My control and target, and I do that teleportation operation. And then I could imagine doing my C0 gate, which you're familiar with this nomenclature. I could do my C0 gate afterwards. And there it looks like a big waste of time because I did all this work. I could have just directly done that control NOT gate directly on the control and target photons. But what's interesting here is that if we think about changing the order of these operations here, then something interesting happens. Of course, you know very well that a feature of quantum mechanics is that it matters what order you do operations in, and we quantify this by commutation relations, and that in general AB does not equal BA. And it turns out that if I were to do this C0 operation back here, then that C0 and these Pauli bit and phase flips don't commute, but the commutation relations are sufficiently simple that I just need to do something like this, and I have the same operation. And that what I've just drawn is an articulation of the commutation relations. So if you write those matrices down, or however you want to do it, you see that you get the same operation there. Does that make sense? And now what's interesting is that if you think about what this gate is, it's this thing here that doesn't work with probability 1. But I've now done it here, where I send a single photon in here and a single photon in here. And in the original conception, the probability of success was something like 1 in 16. And so now I'm in a situation where I have my control photon and my target photon, and I'll implement the C0 gate. Well, I just send each of those things into some sort of storage loop of some kind. And now, while they're sitting in that storage loop, I generate two maximally entangled, two Bell states of two pairs of photons, and I generate two single photons. I send 1/2 of that, each of those Bell states, into this C0 gate, together with these single photons, and it doesn't work. I don't get one photon here and one photon here. So I do it again. I continue to keep the control and target photon in these storage loops. I prepare another two maximally entangled states, I prepare another two single photons, and I do it again, and it doesn't work. And on average, I do that 16 times before it works. But then when it works, I then feed this photon and the other half of this entangled state, and this photon and the other half of this entangled state into these Bell state measurements. And based on the outcome of those Bell state measurements, I do these bit and phase flip operations. And I've thereby turned a non-unit probability gate into a unit probability operation at the cost of producing, on average, 32 copies of this maximally entangled 5+ state and 32 single photon states. Does that make sense? that's pretty neat. I think that's an application of this teleportation idea. And in this KLM paper, they showed that you could using a polynomial number of additional photons, you could make this operation happen and get the exponential advantage from realizing quantum computing. So please ask me questions about that, because I think I'm going to stop.
How would that scale up if you wanted more than two actually entangled photons? You've got the one at 16, and the two, which is quite 4.
So the idea is that this provides a recipe, and this is superseded by other schemes now, but is an interesting sort of historical and pedagogical way of describing things. But the idea is now that you have a deterministic controlled NOT gate, and you can do anything you want with it. And each time you want to run one of these gates, you prepare these additional sets of entangled and unentangled photons, and then you realize a gate with success probability that's arbitrarily close to 1. And so then you can almost put this whole operation into some box and say, all right, every time I want to realize a C0 gate, I've got a recipe for doing it. And so if I wanted to prepare a 10 qubit entangled state, I write down how I prepare that in terms of single qubit and C0 gates, and every time I have a C0 gate, I do something like this.
Are there any more questions?
It's easy for peers to say it's cheap because it's polynomial instead of exponential, but that still sounds very expensive in terms of the number of single photon states you sort of casually require.
Yeah, that's exactly right. Practically, polynomial, it matters whether it's exactly what it is. And in the original KLM scheme, it was very expensive in those resources. So it was polynomial, but it was a very large polynomial, so there was a huge sort of resource overhead. And I guess over the last 12 years or so, that overhead has been reduced by orders of magnitude, and it's been reduced in two ways. One is to look at measurement-based quantum computing. So Mike Nielsen showed that, and maybe I can talk about this in a bit more detail, that this type of linear optical quantum computing is very amenable to that model of computation. And in fact, Terry then showed that you could get a massive reduction in that overhead. And separately, Tim Ralph and Alexei Gilchrist and other people showed that using a sort of a more conventional gate model, you could encode against the errors of this operation and get a similar resource saving. And I guess it was in both cases comparable in 3 orders of magnitude or something like that reduction from the original scheme. So it's much less expensive now. And then, as I hope to get onto when I give you something more like a research talk later on, in terms of practically realizing these things, you shouldn't count the number of photons, you should count the number of photon sources, in the sense that, if you have a device that spits out photons at 1 gigahertz, then every second you get 1 billion photons. So yeah, 1 billion photons sounds expensive, but you've just got one device producing those things. And I guess it's a good point maybe to finish on now, is that this is the price that you pay. So going right back to this list here, you have these very nice low noise systems and this nice ability to manipulate them and so forth, which maps over into this path encoding. But the price you pay is that it's very hard to get them to interact with one another, and so you have to use these additional photons. But I'll hopefully convince you that that the sort of technology is emerging such that, well, if you have to scale these things up, the difference between, you know, having 1,000 photon sources and 1,000,000 photon sources is maybe not so great, in the sense that it's getting from, you know, 10 to 100 that's going to be the real challenge. But once you've scaled it up to 100, then, you know, making 1,000 or 1,000,000 of them is, I mean, it's not, it's almost neither here nor there, if you see what I mean.
Yeah. What I don't quite see is that it's a price that you can pay, and that what crippled you before it doesn't still cripple you now in another place.
No, I mean, you have to have a massively more complicated device. You know, you have to have orders of magnitude more photons than you have actual qubits in your system to do this, to make them effectively interact. And we'll talk a bit more about cluster state approaches, but in there it's the same situation. But you should also think of it as somehow similar to error correction and error encoding, where you have a large overhead in terms of the number of physical qubits versus the number of logical qubits, and it's much the same sort of story, where you have many more physical systems than you actually have logical qubits. Does that make sense?
There are no more questions. We have a coffee break, so let's thank Jeremy.